We're going to look at multiple alignment, and multiple alignment is essentially using more than 2 sequences and aligning them together. So a pairwise alignment, and we saw several different types of pairwise alignments. We looked at global alignment, local alignment, G-local in MATLAB's terms, or free end gap alignments where you don't analyze the end gaps, and then multiple local alignments where you try to find not just one local alignment but multiple. So those are types of pairwise alignments. Okay. In multiple alignment, we are looking at not just 2 sequences but more than 2 sequences. Make sense? All right. Why do we do multiple alignment? Multiple alignment improves confidence in homology. Right? If you have 2 sequences aligned, you may not be as sure about whether their amino acids really mean anything. But if you have, say, 20 proteins aligned and they all have the same amino acid, then that gives you a higher confidence that they are related proteins, and the amino acids that are conserved have something to do with their function. Okay, so we can correct an alignment. So if a pairwise alignment is, even though we have a method that gives us the optimal score, right? So among all possible paths that we can consider, dynamic programming gives us the best answer. Okay, but that doesn't mean the answer we get is the best biologically the best alignment. Okay, so we make a lot of assumptions in the scoring. There are many different substitution matrices. We arbitrarily choose one, which is our favorite, the Blossom 62, right? But if you use a different substitution matrix, you're going to get a different answer. Right? If you are working with in a different species, or if you're working with proteins where the amino acid composition doesn't match the one that Blossom was generated from, then your substitution scores are not going to be as accurate. Okay, and as a result, the pairings of the amino acids that you get from the alignment will not be biologically correct. Okay, we can improve the alignment pairings of these amino acids or of these nucleotide residues if you are working with DNA by doing multiple alignments. Okay, so it just increases the amount of evidence we have for pairing up these individual residues. Right. We can find conserved regions in the alignment. Just with 2, that's not possible. With multiple proteins, you sort of the conserved portions will be more observable. Okay. We can estimate evolutionary distances between different proteins and also predict protein secondary or tertiary structures from the multiple alignment. Okay, and we'll see how this is done later in the course. All right. So the problem is, given K sequences, find an alignment that maximizes the alignment score. Just like with pairwise alignment, when K was equal to 2, we tried to find an alignment that maximized the total alignment score. Right? But here, how do we calculate the alignment score? We have to look at each column. There are many different residues there. How do we sort of calculate a single alignment score? If we take any 2 of them, we can look at the substitution matrix and see the alignment score of that. That's going to give us just 1 score. All right. So one idea is to look at all pairs of residues and then add up their alignment scores, which we'll see in a few slides. And then the resulting multiple alignment will look something like this. You're going to see some columns that are highly conserved. They're going to have residues that are the same or residues that are related. Okay, so some of these amino acids share the same properties, which is why I say they are similar. So in this column, you have hydrophobic amino acids. So they are still conserved residues. Okay, we have a cysteine, which is 100% conserved, and a tryptophan here, which is 100% conserved. Okay, and then you may have some regions that are, as a group, conserved together. So we'll have some conserved residues, which are 100% or close to 100%. We're going to have some columns that share a certain feature, So all those amino acids are hydrophobic, and we'll summarize it as a hydrophobic amino acid. Okay. So for this set of proteins, the conserved pattern can be described as a hydrophobic amino acid followed by any amino acid followed by a hydrophobic amino acid, and then a cysteine, and then range of amino acids, and then tryptophan. Okay. All right. So how do we calculate the alignment score? As I mentioned, it's not trivial, right? If you have a set of sequences, here I have 6 sequences, right? I can calculate the total score, the total alignment score, by doing pairs of alignments. Okay, so I can align A and B, or I can look at the alignment of A and B in that multiple alignment and add up the scores of pairs of amino acids there. And then I can align BD, add up the pairs of amino acids there. So this structure right here is a phylogenetic tree. It relates, it brings the closest proteins together. Okay, so A is closest to B, B is closest to D, and so on. Okay, so it's sort of which protein is derived from which other protein. And that represents sort of the biological history of these proteins. And it makes sense to add up the substitution scores for the related proteins. Okay. But often we don't have a very good idea of the biological history, the evolutionary history of the proteins. So we then simplify it and find one protein that is at the center, and everything else will be related to it. And then we add up the scores of the pairwise scores of everything with A. And this is called a star schema, right? You have one thing in the center, and everything else is related to that central item. In the all pairs way of calculating a score, you look at all pairs of sequences and add up their pairwise alignment scores. All right, so how can we solve multiple alignment problem? We can solve it using dynamic programming, right? Just like we solved pairwise alignment. But let's see what we can do with 3 sequences. For 2 sequences, we had to create a table, and then we filled that table in. Using the solutions to subproblems, we were able to solve the bigger problem. Okay. Multiple alignment is no different. If you have 3 sequences, now rather than a 2-dimensional table, you have to consider a 3-dimensional cube. All right. So each dimension here represents one sequence. So that's my first sequence. And then this dimension is my second dimension, second sequence. And that dimension is my third sequence. So if I go down this way, right, I'm going from I minus 1 to I, which means I'm introducing a letter in the first sequence. The other 2 sequences don't change, therefore they must be gaps. Okay, so this step would give me C gap gap. I advanced in the first sequence, the other 2 stayed the same, meaning they are going to be gaps. Make sense? All right. So the last type of move is going to be the main diagonal, the cube diagonal, going from the opposite corner, where you are advancing in each of the 3 dimensions. That's going to be an alignment of the 3 residues. Okay, C, T, E. So the score of that is going to be the score of that wherever you came from, plus aligning these 3 together. And if you are looking at all pairs of alignments, you would look at the score of C and T, score of T and E, and score of C and E, and all those up. That's going to give you this total score of getting here. Okay? Make sense? All right. So mechanistically, it's no different than your 2-dimensional dynamic programming. You have a list of options, right? Where you are coming from and what the score for that move is, and then you look at all these options and see which one gives you the highest one. Take the maximum. That's going to give you. That's going to be the score of this subproblem. and then you move on to the next entry in your three-dimensional cube. Right. So the fact that we have many more options is not a big deal, right? Right now, but you have to consider how does the number of steps I take depend on the length of the sequences, but now also the number of sequences I have. Okay. So for a for pairwise alignment, we only had to work with a table, and the size of the table was let's assume all the sequences are n. The size of the table was n squared, right? When you increase the size of the problem, the amount of time you spend increases by n squared. When you double the length of the sequences, you quadruple the time. So that's not so bad. Okay, but here we have another thing that we need to consider, which is the number of sequences. Okay, so with two sequences, it's just a table. It's n squared. With three sequences, you have to create a cube, right? You have to divide the cube into all sections, and that's going to give you n times n times n entries, right? So on each face, you have a table, so that's n squared, and then you have many slices of n slices of that. That's going to give you n cubed, little cubes, cross sub problems that you have to solve before you get to the final answer. Okay, so that's n cubed. And then we can take this idea and move on to a four-dimensional system where k is equal to 4. So if you have your number of sequences represented as k, the size of this hyper table that you need to create is n to the power k. Okay. And anytime your problem depends exponentially on a parameter, that's bad. So for pairwise dynamic programming, we had only one parameter, which was n. So 2 is constant, 2 doesn't change. So that's not so bad, right? It's polynomial. But here we have a parameter k. The total amount of time increases exponentially with the number k. So let's say we have a sequence of our sequences are of length 100. Okay, and when it's 100 amino acids, it takes us 1 minute to solve the problem, or say 1 second. Okay, and if I double the length of the sequences, it's going to become 4 seconds. Right, so this is pairwise. Make sense? Right. So for multiple, let's assume that the average length is 100. So we won't try to play with that. And k is equal to 2, right? With just 2 sequences, here also 2 sequences because pairwise. 100 squared gave me 1 second plus times the coefficient. So solve for coefficient times 100 squared equals 1 second. 1 over 10,000, right? And now I'm going to increase and ask if I have 100 to the power 4, how many seconds do I get? And it is, as you said, 10,000. Okay. Now let's increase it to that's 10,000 seconds, right? I only doubled the number of sequences, but the time that I spent increased by 10,000. Okay. So if I increase the number of sequences to, say, by 3-fold and make it 6, that's how many seconds? 100 million seconds. Okay. So I didn't increase the problem by much, right? I only added two more sequences, and the amount of time increased rapidly. Okay, so you can see that I really cannot handle, say, 10 sequences in my multiple alignment if I were to do dynamic programming. The amount of time that I have to spend blows up really fast. So the running time, as I showed you this O notation, which is our way of saying strip out all the coefficients. Those are not important. We are really concerned about how the time changes with the inputs rather than the specific amount of time. So it's for 3 sequences, the runtime is O(n) cubed. For k sequences, there's this coefficient here, and that let's ignore it for a moment. It's really O(n) to the k, right? What we ignored is that it's not just the number of little cubes that you have to solve for. It's also the number of options increasing. Okay. So the number of options also increase as you increase the number of dimensions. For a table, for where you had just 2 sequences, you had 3 places to come from. For 3 sequences, you have 1, 2, 3, 4, 5, 6 places to come from. For 4 sequences, you're going to have many more. Okay? So the number of places, the number of options also increase exponentially using 2 to the power k. So the problem is much worse than we thought it was. Okay. So anytime you see the running time depending exponentially on a parameter, you should know that you really don't have the luxury of having this increase any more than, say, 3 or 4. Okay. All right. So dynamic programming is not feasible to solve multiple sequence alignment problem, which is why all the methods available, they use heuristics. They sort of do their best guess. Okay? They have a strategy and they follow that strategy. One common strategy is to perform progressive pairwise alignments. So we know pairwise alignment is efficient, so we're going to make use of that, and we're going to try to reduce the multiple alignment to a set of pairwise alignments. Okay. It's not going to necessarily give us the best multiple alignment, but it will hopefully be good enough. Okay. All right. So what we're going to do is in a pairwise alignment, at each step, we can align a sequence to another sequence in the input. We can align a sequence to a group of sequence alignments. Okay. So we can have a smaller number of sequences already aligned. Then we can align a new sequence to that multiple alignment. Okay. Where we can expand our multiple alignment by adding one more sequence. Or we can align a multiple alignment to a multiple alignment. Okay. So we have sort of 3 different options, but for each one, we will use a 2-dimensional dynamic programming table. So in this figures, we show a schematic of how this is done. We first align the red and the blue sequences, and then we get a multiple alignment that will then act as if it's a single sequence. Okay. Then we align that with the yellow. This alignment is again pairwise alignment. Okay, so very efficient and in the order of n squared. The green and the pink are aligned. We get one alignment that will now act as if it's a sequence, and then align that with the other group to get our final alignment. So how do we decide which 2 to align first? So I can go through and look and align the ones that are most similar first, because I'm less likely to make a mistake or have an error if I start off with the ones that are most similar. The ones that are most similar are going to be easier to align. They're going to have more of their characters identical, and their alignment, I can be more certain that their alignment is correct. Okay, so I'm going to align them first. Each step, I'm going to find the next closest pair of sequences and align them, and which is why you get a tree structure like this. So the order of the alignment matters. Let's look at this hypothetical example where we need to align ABA, BB, and ABB. Okay, so these are 3 sequences. Now, if we align ABA and BB first, and we can either get, let's see, we can either get this alignment, or this one, right? As far as aligning ABA with BB is concerned, those two have the same score. They have the same pairwise score, right? So this is a pairwise alignment. If you add up A with a gap, B with a B, A with a B, A with a B, B with a B, A with a gap. So the total score of these two are the same. So you would arbitrarily pick one or the other, okay? But when we add the third sequence, the total alignment will be different, okay? So if we align ABB to this, we end up getting the best alignment is this, right? So let me also mention that once you align this in a multiple alignment, in a progressive alignment that is locked in, you can no longer break apart A and the gap. You can no longer break apart B and B. You can no longer break apart A and B. So those pairs of things, they act as one character. Okay. We're not gonna shuffle the two sequences anymore. They are locked in. If we place a gap when aligning this, the gap will have to be added to both of them. All right. Okay. So aligning this, now you can see that there is the total alignment score is now different, right? So here and this one, you've aligned A with an A, so that's good. You've aligned A's with gaps, that's bad. All the B's align, and then A, and then BB. Okay, so I'm not gonna do the. Let's do match and mismatch, match, mismatch, and gap. So we have how many matches? We have 1 match, 2 match, 3 match, 4 match. Wait. That's 1, 2, 3, 4, 5 matches. Right? How many mismatches do I have? I'm gonna just consider gap also as a mismatch for simplicity. I have 1 mismatch, 2 mismatches, 3 mismatches, 4 mismatches. Make sense? Okay, so let's look at the other one. I have 1 match, 2, 3, 4, 4 matches, and 1, 2, 3, 4, 5 mismatches. Okay. So this one is better. I have more matches than mismatches. So the total pairwise alignment score will be higher for that one. But because I committed myself in this step incorrectly, I ended up getting in this step incorrect. I ended up getting a worse alignment. So the order of the alignments matter. If I were to align these two together first, then there's just one path. I'm more likely to find the correct answer. Okay. So ABA align with ABB first, lock those in, and then align BB with that. So the general strategy is to use the most similar sequences first, for the ones with the highest alignment score, align them first, and then move on. Okay. And you guys, you should be able to sort of write code for this if you wanted to. So what you need to do to implement this is you have to define the table not just from sequences, but also for groups of sequences. So what do I mean by groups of sequences? So when we create our game table, as previously we just had one sequence on the top, A, C, C, T, and then G, A, T, let's say. Okay. So we aligned those two, and then the alignment path gave us the best answer. when you have groups of alignments, rather than just having a single sequence here, you have a pre-aligned set of sequences. So let's say A, C, gap, C, gap, and then T, T, T. So this is one pre-aligned set of sequences. Okay, and let's make this one too. G, G, gap, T. This is another set of sequences. Okay. So what we need to do now is we have to define our game board where each square represents possible alignment of this column of characters with this column of characters. Make sense? And one answer to that is pair them all up, look at the substitution matrix, add up all their scores. So what is alignment of A with a G? What's the score of that? What's the alignment of A with a G? Add up A with a G, add that up, A with a G, add that up, and then that. Okay. We have 6 substitution matrix lookups, and then add up all their scores. You get the total score for how much money you would make if you were to go to that square from a diagonal, meaning if you were to match up that column with that column. And a gap in this case means introducing a gap in the entire column here. So let's say gap, 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 without breaking apart the individual characters. So the coding is very similar. The only thing you need to change is how the game board is set up. Rather than looking up the substitution matrix once, you look at the substitution matrix for every pair of characters from the 2 sets of sequences. All right, so this strategy is good, but it's prone to making mistakes early on, especially if an incorrect choice is made for picking out the 2 sequences to align or the 2 groups of sequences to align. Okay, so if your tree is not the best tree, you may end up getting a not so good alignment. Okay, and also the errors that you make at any point, they propagate, because at a later step, a new sequence may provide you evidence that something that you aligned previously was not a good idea, but because you committed yourself, you're not going to break it apart, and that's a problem. The progressive alignment is fast, but it doesn't necessarily give us the best answer. There's a method called Saga, which works well, and it uses genetic algorithms to solve the multiple sequence alignment problem. So the idea is to take alternative solutions and consider them as a population and sort of do a natural selection on them. The best ones will survive, the ones that are not so good will die out. And we're going to have a concept of crossovers, a concept of mating different solutions, also mutating solutions to generate new alternative solutions. And then at each generation, we're going to keep the best ones and kill off or by natural causes, the ones that are not so good will die out. So only the ones that are fit will survive and will create new children. So at any time, we have a population, and this population is encoded as a binary string. But depending on the problem you are working on, the population, each individual can be, say, a set of numbers. It could be a binary string, or it could be, in our case, a multiple sequence alignment. Okay? So one multiple sequence alignment will be one individual in the population. Now, in our multiple sequence alignment problem, there's a process of selection where we go through the individuals in the population and we see their fitness values. For each one, we calculate a fitness. In our case, the fitness is going to be their total alignment score. Okay? The sum of all pairs of alignment score, substitution score will give us the total alignment score. We're going to select the fittest individuals, get a pool of them, and then some of them will mutate, meaning we're just going to modify them a little bit. And some of them will pair up and do crossovers to create the population at the next generation. Okay, so this Tn is one generation, Tn plus one is the next generation of individuals. Okay? And then we're going to repeat this process over and over for a number of generations. And as a population, their fitness values will increase over time, because at each step we are adding some randomization, but we are only keeping the ones that are fittest. And over time, we'll end up with individuals that are more fit than what we started with. Okay, so this is the general idea behind genetic algorithms. When you want to apply it to your particular problem, there are several things you need to do. The most critical aspects are how do you introduce mutations and perform crossovers. Okay, so for multiple sequence alignments, there are, in Saga, they've defined two sets of crossovers. Okay, so in one of them, so if this is your one sequence and this is another one, you can select, say, the first block from the first solution, the last block also from the first solution, but the one in between will come from the other solution. So you're sort of combining two solutions, creating a new child. So when we have two individuals, okay, this is, let's call this one mother, and this one is the father. All right. So we're going to do a one-point crossover. In the mother's solution, we are going to just arbitrarily pick a random, and everything to the left of that random position will be going to one child, and everything to the right of that will go to the other child. Then we're going to combine that with the corresponding parts from the father's genome. Okay, but how do we do that? Let me zoom in so you can see how this is done. So when we introduced this random crossover point, right, the first sequence we kept its WGKV characters. We're going to scan the father's genome for those characters as well. So that's our first sequence, WJKV, which means we're going to cut this sequence at that position. Okay. Second sequence, WDKV, which means we're going to cut it at this position. Okay. So you need to make sure that you sort of scan, and as soon as you find the V here, that's where we cut. WGKV again, we're going to cut it here. WSKV, we're going to cut here. The mother sequence could have had gaps in the first part, but in this case it doesn't. The process would be the same. You want to look at what portion of the first sequence you've consumed and made it part one. You're going to take the rest of it from father's genome. So when we take the rest of them from the father's genome, NVD, before we add it, we have to put some gaps in. Okay? And how many gaps we put in will depend on where the other sequences get cut up. All right? And you can sort of see that there's going to be like 2 gaps here, so we put 2 gaps. Get the second part, but flip it. And when you flip it, MATLAB will automatically fill in the gaps for you. So if I'm creating a matrix, and I'll start empty at the beginning. Then I'll add the first row, I'll just add 3 characters. Now for the second row, I add 5 characters and say gap, B gap, C gap. MATLAB automatically extends the first line with 2 spaces for me. Okay, so it automatically adds these sort of gaps, but it's flipped, right? So you have to make sure that you add your strings in reverse order, and then after you add all the sequences, you're going to go back and say find all the spaces, replace them with a gap. So anytime it doesn't show something, it's going to be a value 0. And then we replace it with gaps, and then you can flip before you glue it to the first part of the mother. This portion comes from the mother. This portion comes from the father, finding the cut side and then gluing and then adding gaps if it doesn't fit all the way. And then this part is going to be the second part of the second child, and then the first part of the father makes up the first part of the second child. All right, so we got 2 children. We are going to calculate their fitness value and select the one that is fitter. So whichever one has the higher pairwise alignment score, we're gonna total pairwise alignment score. We're gonna keep that one. Okay, so once we have a multiple alignment, what can we do with it? Getting a position-specific scoring matrix is something that we do to summarize a multiple sequence alignment. Okay, so multiple sequence alignments are sort of, in a way, not standard, right? Depending on the number of sequences you have, your matrix could be 100 rows if you have 100 sequences. It could be 50 rows if you start off with 50 rows, right? So it's you can't really compare different sequence alignments very easily that you generated from different protein sequences. Okay, so what we would like to do is summarize the columns and write down their amino acid composition rather than keeping the multiple alignment itself. Okay? So this position-specific scoring matrix will then be a summary of the entire multiple sequence line. All right. So what is a position-specific scoring matrix? A position means a single column. Position-specific scoring matrix means how you would score an individual position in your protein based on the composition of amino acids that you expect to see in that column. So let's look at this example sequence alignment. It's a DNA sequence alignment, so you see ACGTs. The portions that are highly conserved are shown in red, just for visual purposes. Okay. And then we create a table where we list all possible nucleotides in rows. If you had a protein sequence, you would have 20 rows because of 20 amino acids. Now we have 4 rows because we are working with DNA. And then each of the entries here will represent how many of each nucleotides you have in that column of your multiple sequence alignment. Straightforward, right? Okay. So here I have 3 A's in that column, which is why I wrote down 3. And I have 1 C, there's the 1 here, and there's no T's, so there's a 0 there. And you go through and fill in this entire table. So for any multiple alignment, you will then get a matrix that has 4 rows. And it's sort of conventional to convert that into frequency matrix. So this is sort of a count matrix. And we're just going to divide it by the total number of sequences to get the numbers adding up to 1. Each column will add up to 1. In the first position, 60% is A's, 20% is C, 20% G. All right. So now if I get a new protein and I sort of ask, does this new protein fit to this family of proteins? What I would do then is see if it follows this position-specific scoring matrix. Okay, so if my new sequence is, let's say, C, and then A, T, and let's pretend my alignment is only 3 characters long. Okay, so ignore this part. So ignore this part. I'm only looking at CAT. What I would do is I would look at here. C is 20%, so observing a C here is 20% good. Make sense? I'll take 0.2. That's sort of, in a way, probability value. And I'll multiply that with A, which is 0.4, and T, which is 0.8. And this will give me sort of a probability score of CAT belonging to this family. It's I get a probabilistic scoring using the frequencies of these different nucleotides being observed in the multiple alignment. The problem here is the zeros, right? So if I have a protein that has T, A, G, T, okay? So what happens is everything here were really good, right? So this is 0.6, this is 0.4, and then 0.8, 0.6, 0.8, and then 1, and then 1, 1.0. Okay. So everything was had really high scores, except for this T at the beginning, which had a 0. When you multiply everything, you'll end up 0, even though everything here had really high scores. Just because you had 1 0 made everything have a total score of 0. Okay? So zeros are not good because they sort of cancel everything out. The fact that I have 0 here may just be a consequence of the fact that the proteins that I used were not representative of all the possible things in nature. Okay? I looked at 5 sequences. If I were to look at, say, 1,000 sequences, there may have been some T's there. So statistically, I want to be able to do something with these zeros so they are no longer zeros. We're going to learn about strategies for modifying those zeros. So the basic idea is find the frequency, find the number of amino acids in a column, and divide by the total number of sequences. So that was the matrix that you saw. Number of residues of type A in that column, divide by the total number of sequences. So that is not very good. What we will rather do is use pseudo counts, which means that even if we don't observe a T in that column, we'll always pretend that we have at least one representative of each character in each column. So adding pseudo counts is, in a way, adding 4 sequences here. Sequence 1, 2, 3, 4, where your first sequence is all A's, your second sequence is all G's, and your third sequence is all C's, your fourth sequence is all T's. Okay? That way, you will always have at least one T in each column. You will always have at least one A in each column. So I've added 4 fake sequences that are all A's, the first sequence, all G's in the second sequence, and so on. So pseudo counts is you would add a 1 for each type of amino acid or for each type of nucleotide, even if it doesn't exist. Okay. And then the bottom part, because we added 4 fake sequences, or in the protein case, you added 20 fake sequences, you've artificially increased the number of sequences, so you add plus 20 when divided by the total number of sequences. Make sense? All right. So one might argue that this, even though this is a good start, rather, why do we add 1 when we are adding considering a tryptophan which doesn't exist very frequently, we shouldn't add a 1 for tryptophan. We should add a smaller number for tryptophan. Okay, because it's less likely to be a tryptophan by chance. So we can incorporate the background distributions of amino acids in our pseudo counts. So this is a slightly more improved approach. We will look at the background frequencies of each amino acid and multiply it with a coefficient which controls the amount of pseudo count that we add. And the next level of improvement is using a substitution matrix, so that when we observe, especially in proteins, a certain set of characters, the amino acids that are similar to those are more likely to be added as pseudo counts than the amino acids that are not similar to those. Okay? So the substitution matrix represents how interchangeable amino acids are. We can incorporate that when we are adding these fake counts to our position-specific scoring matrix. Okay. All right, so other strategies are to give extra weight to highly conserved residues, to lower the contribution of certain counts if you have enough data, right? So if you have 1,000 sequences, then your sequences are more representative of the of nature, but compared to having just 10 sequences. So adding pseudo counts is important. It's more important for when you have 10 sequences because you don't have a good sample. Your 10,000 sequences are more representative. You don't really need to add pseudo counts, so you can reduce the factor that you have for the pseudo counts so that it doesn't affect your results as much. Okay. Another strategy is to weight the sequences themselves, and that's especially important when you have highly similar sequences. All right. So if you are looking at proteins from different species, some species are more studied than others. Right. So species that are more similar to humans tend to be better studied. The rows that you have some rows will be very, very similar to each other. Okay. So if you have, say, different subspecies of chimpanzees or chimpanzees that are very close to each other in evolutionary history, you have their sequences in your multiple alignment. They're going to be near identical, and they will sort of dominate your frequency matrix. So what you would do then is reduce the contribution of those sequences. So rather than adding 1 for each of them, you would say add half for each one. Make sense? Okay. So that's how you account for very highly similar sequences. Once we have the sequence position-specific scoring matrix, that itself can be used as a summary of the family of proteins, and given a new protein, we can ask the question, does it fit with that family? And based on that probability, we can say yes or no. Another method to use these matrices is to create sequence logos. And this sequence logo is generated by looking at the amino acid composition of each column. All right. So the height of each amino acid represents how conserved that amino acid is in that column using this formula. Okay. So the entropy of a column is the probability of an amino acid, or the frequency in this case, times the log 2 of that probability. And you add up for all amino acids. Okay, so let's look at nucleotide sequences. So this is 0.6, 0.2, 0.2. So for the first column, the entropy is the following. It's going to be the sum of 0.6 times log 2.6 plus 0.2 times log 2.2 plus 0.2 times log 2.2. So it's going to give you the entropy. When you have 0, you don't add that up because log 2 of 0 is not okay. All right. So you're going to multiply the probability with log 2 of probability. That gives you the entropy of that column. Make sense? So let's look at the column that has all t's, where the frequency of t is 1.0. So you're going to do 1 times log 2 of 1, 0, right? And 0 times 1 is 0. So the total entropy of that column is 0. The lowest entropy you can have is 0. What's the highest entropy for the DNA sequences? Let's just double check. So the highest entropy is where there is highest disorder, right? Everything is random, so when everything is random, you'll have 0.25, 0.25, 0.25 for each one. You're going to have 0.25 times log 2 of 0.25, and you're going to have 4 of these. So you have to add a minus, and then you get plus 2, all right? The numbers will always be negative if you don't put the minus, right? The entropy will vary between 0 and the highest number will depend on how many characters you have in your alphabet. Okay, make sense? For proteins, if you have 20 amino acids, this is going to be 1 over 20, right? Each one has a probability of 1 over 20. This will be 1 over 20, and you're going to have 20 of them. And the highest entropy is 4.3. So the amount of information is the opposite of that. So the amount of information contained in a column is the opposite of amount of disorder. If you have a column having all A's, that has the highest information. If they are all random, you don't have any information for that column. So you have the least amount of information if it's all random. So what we do to get the information is we subtract the entropy from the highest possible value. For proteins, that's going to be log 2 of 20. For DNA, it's going to be log 2 of 4. Okay, so what is it? 4.3 minus the entropy. When the entropy is 0, meaning you have just one type of character in a column, the highest information is going to be 4.3. So your column may contain multiple amino acids, right? If you have just one amino acid, like here, or one character, what you would do is show that character as the tallest. Say this D, if it is the only character in that column, its height will be 4.3. Okay. So that's 4.3. If you have two characters, then you have to adjust their heights accordingly. So what we do is we're going to multiply the amount of information contained in that column by the frequency of each character. So let's look at, for example, this E and D. Okay, so if you have a bunch of E's and then a bunch of D's, the information content is going to be 4.3 if it's just one character all the way. As soon as you have another character, the total height is going to be less than 4.3. Okay, so we're going to find the information content first, and then we're going to multiply that. Here, let me add one more E. Let's say the information content is 3. Okay. We're going to multiply 3 with 4 out of 7 times 4 over 7. That's going to give us the height of E's, and 3 times 3 over 7 will be the height of D's. So within a column, you would adjust the height of the characters by multiplying its frequency with the total information content for that column. All right. When you have just one character, the frequency would be 1, and then it would have just itself. Another way to summarize multiple alignments is by creating regular expression patterns. So I showed you this example where we took a multiple sequence alignment, we looked at the columns and sort of kept the parts that looked similar. And then if we couldn't find anything common for that column, we replace it with an X. So if a column appears to be sort of random, we replace it with an X. If it's conserved, we keep the character that's conserved. Pro-site patterns and sequence logos will sort of look in a way similar to each other. If you convert a sequence logo to a pro-site pattern, what you need to do is sort of have an idea of a threshold. Say, I will only keep the characters that are taller than 2.5. Then I'll say there's a G there, there's any character, and then any character, and then a P. That's going to be the motif for that portion. Okay. There are other rules that sort of, instead of an X, looks like I could have a G and A. So they would have rules for anytime the height of a character is more than 1 bit, I would include it as an option in that column. All right. So that's how the pro-site patterns can be generated from multiple alignments. So X in the pro-site pattern means any character. When you have square brackets, it means any of those characters. When you have curly brackets, it means anything but those characters. When you are converting this to MATLAB regular expression or Python regular expression, they use slightly different way of encoding these. So an X is encoded with a dot in MATLAB, in sort of regular expressions that we use in programming. This is the same. The curly brackets is represented using square brackets followed by the hat symbol. Okay, so that's the anything but A or M. All right. So square brackets followed by a hat means anything but. And then in ProSite, they have X parenthesis 3, which means 3 X's. In MATLAB, we write that by X curly bracket 3. In ProSite, X parenthesis 2, 4 means it could be 2 X's, 3 X's, or 4 X's. In MATLAB, we do that by saying X curly bracket 2, 4. At least 2 X's, at most 4 X's. All right, so next we have the less than symbol, which marks the beginning of the sequence, and the greater than symbol, which marks the end of the sequence. So if you have a pattern that you know has to start with the beginning of the sequence, you have a smaller than sign. If a motif is found somewhere in the middle that matches, that's not going to be a match. All right, so we are enforcing that this motif be at the beginning, and that, for example, could be true for subcellular signals where you have a tag that targets a protein to go to, say, mitochondria. These are just some examples. A or C followed by anything, V followed by 4 if anything, and then anything but E or D. So that says I'm looking for an alanine or cysteine at a column, followed by any amino acid, followed by valine, followed by 4 if anything, followed by anything but glutamine or aspartate. And the next example says I'm looking for a protein that starts with alanine. Okay, so the first character of that protein has to be A, followed by anything, followed by serine or threonine, and I'm looking for 2 of them. Okay, so which means serine or threonine, and then serine or threonine. Okay. So you could have S and T, you could have T and T, you could have S and S. They will all be matches to this portion. And the next thing is followed by an amino acid or no amino acids. So if I have AWSSV, that is a match because I have SS, which matches this portion. I have nothing that matches that portion, and I have the V. This would also match AWSS, say, LV. Again, SS matches that, and then the L would match this portion. X01 means I could have something there, or I could have nothing there. And then V. You would do regex, and then your sequence that you are trying to search in. And then I gave you this sequence, and I asked you, does it contain this pattern? You could look at it by hand, or you could write your regular expression and ask AC followed by anything, followed by a V, followed by any four things, followed by anything that is not an E or a D. So that's the pattern that you would write in MATLAB. And then if it finds it, it'll tell you the location. If it doesn't find it, it'll tell you, no, I couldn't find it. So this pattern is not present here. Let me just confirm this. There's one candidate here, so A matches that. Any character T matches that. V should match V. 4 of that should match that portion. And there's an E here which conflicts with the description of not an E or a D. Okay, so if I were to change that E to something else, let's say Y, now it would match. It says there's a match at the 4th position. Let's show the match. That's where it matches. Hidden Markov models are, they include states and transitions. The transitions between states is described probabilistically, and each state can emit something, in this case, emit a character which will represent, in our case, an amino acid. Okay. So this figure shows an HMM, a hidden Markov model. Okay. So there's a start position and an end position. The entire thing represents sort of a signature. Okay. And this signature has been created from a set of known sequences belonging to that family. So we have match states here. These match states will be sort of responsible for emitting an amino acid character. When we are at M1 state, the amino acids are emitted, are sort of outputted by this distribution. Okay, so a proline has the highest frequency by 80%, but the other amino acids have a small probability. You can see the histidine has slightly more than the others. Okay. So we expect that M1 on the average will emit a proline most of the time, but other amino acids can also be emitted when we are in M1 state. Likewise for each of the other match states. So when we are in M2, alanine is the highest, is the most likely amino acid, but other amino acids can also be emitted. M3, threonine, M4, histidine are the most likely amino acids. Let's consider a path through this sort of machine, through this model. We could start from here, and then we could go to deletion state, go back to M2, and then let's go into delete again, D3, M4, and then go to end. If we go to D1, that means we are skipping match 1, right? There's going to be a gap there. And then we go to M2, we're going to emit one of these amino acids by random. So rather than A, let's say we get a Y. Then let's go to D3, which is a gap, and then go down to M4, which will be, say, an S. All right. So the chunk of sequence that we have represented is Y and S. It wasn't the most likely sequence, but it is a sequence that can be generated from this hidden Markov model. And we can calculate the probability of YS being generated from the HMM. When we are at a state, transition to all the other states will be described using a probability distribution. Okay, so we're going to have a table for the start that will say going to D1 is 50% likely, M1 is 40% likely, and I0, which is the insertion, is 10% likely. So we're going to have a random number generator that will 50% of the time take us to D1, 40% of the time take us to M1, and I0 will be 10%. We are trying to find the probability of going from start to end. If I asked what is the probability that YS can be generated, there are many paths that can lead to an emission of YS. So what I could do is I could go like this and have this generate Y, have this generate S. That's one way, right? I could also go like that, and then like that, have this emit Y, have this emit S. I could also go like this, have this emit a Y, have this emit an S, and go to the end. So each of those paths will have a probability associated with it. So this will be 10% multiplied by the probability. Well, once I'm there, I'll assume that I have a Y. Let's simplify. And then multiply that with M1 emitting an S. What's the probability of that? It's a very small one, let's say 1%. So we have 10% times 1%. What is the transition probability going from M1 to D2 versus M1 to M2 versus M1 to I1? Okay, so again, that's going to have a probability. We're going to multiply that, multiply that, multiply that. Once we go to the end, that's going to be the probability of generating YS following. So since there are many different paths going from start to end, generating YS, each of them will have a different probability value. What we need to do is we need to add them all up. That's going to give us the total probability that a YS can be generated from this machine. So the number of paths is it a feasible thing to do, or is it not? So at each state, you have roughly 3 options. So if you have 3 options here, and then 3 options here, and then 3 options here, the total number of paths is going to be 3 to the power n. And anytime you see the size of the problem being in the exponent, the amount of time that it would spend going through every path will grow exponentially with n. You will not be able to solve larger problems. Okay, so you may be able to solve problems that are, say, 3 or 4 length, but as soon as it goes to 10, you're going to run into problems. So how do we solve this? Using dynamic programming. All right. So a hidden Markov model is usually generated from a multiple sequence alignment. First, you take your set of sequences, align them multiply, and then fit the model to the columns of your multiple sequence alignment. So the generation of the model is sort of beyond the scope that I'm not going to describe. But let's think about how we can calculate these probabilities. So to calculate the probability of, say, generating YS from this model, what you would do is you would break up the problem into smaller problems. And then we will then ask, what is the probability getting here following any path? Getting here from any path, there's only one path that was 50%. What's the probability of getting to I0? That was 10%. What's the probability of getting to M1? That is going to be, we have 2 different ways, right? This way and that way. Using those two ways, we're just going to add up those probabilities. If you are looking for the most likely path, you would take the maximum. If you want to look at the total probability, then you would have to add up the probabilities. Okay, so let's think about the most likely path, which is easier. So for M1, we're going to look at the 40%, which was this guy, and then getting to M1 through I0, which is going to be the score of I0 multiplied by the transition probability from I0 to M1. Okay, so let's say that's another 10%. 10% times 10% is going to be 0.001. 0.1 times 0.1, okay, which is going to be 0.01. That would be the probability of going to M1 through I0. So that's clearly less than going from start to M1, which was 40%. So what we're going to do is, in each state, we're going to record the probability of that state and the most likely move that led to that state. So just like in the dynamic programming table. The most likely path is that one. The score, the total probability is 40%. The most likely path is that. Score is, this one was 50%, 40%. And this, we will not use it anymore. It was 10%, but it doesn't lead to M1, so that's ends there. So to get to D2, we're going to consider these two options. And whichever one highest, we're going to keep. And you do that for starting from left to right for every state. When you get to the end, by the time you get to the end, you will have the probabilities of D4, M4, and I4 already calculated. And you're going to say, if I were to go to the end from D4, the score would be the probability of D4 times the probability of this transition. We'll take that. That's going to be one option. And then going through M4 is going to be the probability, the total score, the amount of money that I have collected when I got to M4, times the probability of this transition M4 to N. That's going to be another option. And then I4, another option. You would use the maximum of these three. That's going to give you the final score and also path. And then you would backtrack to the beginning, following the set of paths that give you the maximum value for each state. That's going to give you the final most likely path. So the idea is very similar to the dynamic programming table that we use for sequence alignment. You build solutions to smaller problems, and by the time you get to the end, you have the solutions to the most previous problem that you used in solving the final problem. And you have to, of course, consider the emission probabilities as well for this case. So when you're at M1, you're going to consider what's the probability of M1 emitting at letter Y, and then that's going to be looked up from this table. So each path can generate a different sequence. Path represents the one that has the highest probability, but your HMM can generate other sequences as well. That's why it can represent other sequences as well. They're not going to be, their probability is going to be lower. Each score that you get is sort of representing the probability that HMM can generate a particular sequence, the sequence that we submitted. All right, so the main advantage of PSSM over a model like ProSite is that the gaps are position dependent. Okay, so the transitions that you have here essentially means how favorable a gap is at that position. When we did sequence alignment, a gap was scored, say, -10, regardless of where it was in the sequence. But in reality, you don't want to put gaps, say, in the middle of an active site. Okay, that's going to mess up the active site structure. So HMM will capture that, because then this D2 would have a lower transition coming into it, which essentially means it's not favored. Plus, you get the probability distributions at each step, so that's another advantage. So to solve the most likely path, we use the dynamic programming, and that's called the Viterbi algorithm. So if you search online for Viterbi, it's going to describe the process that I just mentioned. You, at each step, find the probability of getting to a state, and when you try to find the probability of next state, you make use of the connections getting into that state and use the largest one. The probability of a sequence being emitted has a very similar strategy, and those are called forward or backward algorithm, and that essentially sums up all the previous paths rather than taking the maximum. If you are trying to find the most likely path, you use the maximum, right? Because you're asking the question, was this path better than the other path? You have to make a selection. When you are calculating the total probability of the sequence being emitted, you don't really care whether the sequence was generated using one path or the other. You are interested in the ability of the hidden Markov model as total to emit that sequence from any path that it can take. Therefore, you take the summation of all the probabilities leading us. So when you have the three options, and you ask what's the probability of a sequence being emitted, you add these up. When you are asking what's the most likely path, then you have to select one of them. So how do we actually create the hidden Markov model and calculate how are these graphs generated? So if we are given a hidden Markov model, we can fit a new sequence to it. But how are these hidden Markov models generated in the first place? The process of generating these are, roughly speaking, start with a multiple sequence alignment. So in your multiple sequence alignment, some columns will contain letters, some columns will contain gaps and letters. So we're going to have an idea of, say, if a column contains more than 80% something, not other than a gap, we'll call that a match state. Once we identify the matches, the structure of our HMM sort of is generated from these matches. So we fill in the middle part. So this is M1, that's M2 column, this is M3, and so on. So M1, M2, M3. And you put your gaps in and your insertion states in just like in that picture. So once you identify the number of matches from the columns that have mostly letters, and the rest of it, you just put your bubbles, and that's going to be the overall structure of your HMM. Okay. The probability tables for these M's is also straightforward. What you would do is look at a column and see what is the percent of A's, what is the percent of other letters in that column. And that's going to give you those histograms that I showed you. Okay, so this is going to be M1's histogram, M1's distribution of amino acids being emitted when I'm in M1. So that's also straightforward. The next problem is calculating the transition probabilities. So when I'm at the start state, what is the probability of going to that? What's the probability of going there? What's the probability of going there? And again, you can look at the composition of that column. How many times do you have gaps? How many times do you have insertions? And make use of that to decide the transition probabilities of these arrows. It's slightly more complicated than this, but that's the basic idea. And once you've constructed your hidden Markov model, this hidden Markov model acts as a signature representing the entire multiple sequence alignment. When you query another protein, rather than trying to find all the proteins like we do BLAST, what we'll do is we'll say, does this new protein have the same signature, sort of the essence that these proteins have? Okay. By fitting to the HMM and calculating the probability of that sequence being emitted by the HMM.